Hey everyone, so we're going to be talking about the next part of this topic, which is all about chemical potential and the Gibbs distribution. So, starting off with the chemical potential, what we're going to do is we're going to talk about a system where they're not only in thermal contact, but they're also going to be in what we call diffusive contact. This basically means that particles are now going to be allowed to transfer between the two systems. I'm trying to think. Uh, that would pretty much make this an open system between the two objects, but it's still going to be isolated around the environment. All right. So, as we all know, energy always flows from, or at least with the heat energy, heat always flows from a high temperature source to a low temperature source. Well, as you also probably know from countless other classes, especially any sort of EM course or even Physics 125, where you talked about energy, you should know that particles will always flow from a high potential to a low potential. Now, what we're actually going to focus more on, though, is the chemical potential aspect. So, you know, and when you learned in 125, you've probably learned that objects of mass will move from a high gravitational potential to a low gravitational potential, or electric charges will go from a high electrical potential to a low electrical potential. Here, we're just going to be looking at the chemical aspect of it. Now, this is essentially how batteries are working. So you end up having one end of the battery has a higher chemical potential than the other end, and that's what's going to cause the electrons to flow from one end to the other. All right, so we have our two systems, S1 and S2. They're going to be in thermal equilibrium with the reservoir so that the entire temperature of the two systems are always going to remain constant. And as we know, the number of particles in total between S1 and S2 will end up being constant. It will end up remaining the same throughout the diffusive transfer, if you will. So while the number of particles for system 1 and the number of particles of system 2 might end up changing, the total number of particles will remain the same. Now, we learned about the free energy from before, and one of the things that we found was that when a system goes towards its thermal equilibrium, um, the free energy will always end up reaching a minimum value. So we can do that same thing here. So the free energy of the in total is just the sum of the two free energies of the two systems, S1 and S2. And again, this was the equations that we got before. So it's the internal energy minus the heat added to the system uh, of system 1 and of system 2. Now, because we're going to want to figure out the minimum, we're going to take the derivative of both and set that equal to 0. And then what we're going to do, if you remember, one of the ways that we can kind of uh, analyze these equations is we can multiply both of these terms with dn1 over dn1, dn2 over dn2, and then bring that denominator part underneath so that this turns into a derivative or a partial derivative of the free energy in system 1 with respect to the number of particles in system 1. And then same thing for system 2. Now we know that the number of particles gained by one system is going to be equal to the number of particles lost by another. So dn1 and dn2, these two numbers, are actually going to be equal and opposite. So as it says right here, this is just the negative of dn2. What that tells me is that I could pull out the dn1 and dn2 for both. I'd have to include a little negative here because essentially I'm replacing this with negative dn1. And I pull it out from both terms. And then again, I can start solving this and get that in this process, when it reaches thermal equilibrium and diffusive equilibrium, this partial derivative of the free energy with respect to the number of molecules for both system 1 and system 2 should end up being the same, or being equal. So this is one of the statement, though, what they say is the statement about the free energy when it reaches its equilibrium state. Now, we are going to actually define that term as the chemical potential. That way, what we can say is that the system reaches equilibrium when the chemical potential of the two systems are equal, which does kind of make sense. Again, if you have, if we think about more the gravitational potential aspect, if you have a height, if one end is at a higher height than another end, then it will always end up, objects will always end up falling down that slope, down that height difference. And you won't get equilibrium until those two heights are equal, are balanced, until the gravitational potential is the same. And it's the same thing here. The particles, the diffusive equilibrium will end up stopping its transfer once the chemical potential difference goes away. So this is our definition for diffusive equilibrium, that the chemical potentials of the two systems will end up being equal. So this and then the thing about the temperatures being equal will give us an idea of when the entire system is going to end up being in equilibrium. Now, it says here, I don't know why this is blocking it, but what it says here is essentially that if we end up having different chemicals within the system, that the chemical potential will just be the same thing, but what we would do is just have it be with respect to the number of molecules of that specific chemical. That's pretty much all it's saying. All right, so we can get another equation for the chemical potential, so that it's not just a partial derivative of the free energy, by going back to our equation for a monatomic ideal gas. So if you remember, we had this equation for the free energy as a function of the number of molecules and the partition function. So I remember that the partition function Z1 was given by this equation. So the chemical potential is just taking this and taking the derivative with respect to n. So this first part's fairly easy. It's just all we do is drop the n part. But this one we're going to have to pull out one of our I can't remember if it's this. I think a Stirling approximation. Take the Stirling approximation and take the partial derivative of it to get this. And then simplify, move some things around. What we're going to say is n is much greater than 1. So this entire term is going to end up dropping out. And then it ends up simplifying to ln of n over z1. Recombining some of the terms for what z1 is. And we can actually now write the chemical potential in a much simpler term that looks like this. So now, instead of having the chemical potential strictly dependent on the free energy, we now have it on stuff that we can actually calculate fairly easily, like the temperature, the concentration, and the quantum concentration. I just want to reiterate once again, as I've said previous times already, that what you're going to notice is that every time we bring in a new term or a new definition of something, what we're going to end up doing is developing multiple equations so that we can create, as I've said before, a nice web of equations. So instead of just having one route to go between to get to the chemical potential through free energy, now we are coming up and finding a new route to the chemical potential. And what we can do is actually probably fool around with this. I'm pretty sure we're probably going to add in a few more equations, but we want to try and get multiple ways that we could get to this chemical potential so that no matter what information you're given, there'll be a way to get to every other aspect. As I said, it's a nice intricate web that we're creating of interconnected equations, things that lead us from one variable to another. All right. So yeah, this ends up going back to the whole chemical potential being related to the concentration, which again, makes sense. Um, if we have two rooms and there is one room that has a much higher concentration than another room, then it makes sense that the room that has the high concentration should have what we state as a high chemical potential. And as we all know, that high concentration room, particles will start to leave from that high concentration room into a lower concentration room. So, just as we said before, the chemical potential, the particles will move from a high chemical potential to a low chemical potential. And it will stop once the concentrations are equal or once their chemical potentials are equal. So sometimes it might help to kind of rephrase some of the things that we're talking about in slightly different terms. Like if you're having trouble with the whole chemical potential aspect, you can think of it in terms of, particle concentration. You have a lot of particles here, not that many there. It's going to transfer. Um, so you can do that, and that might kind of help out with some things. All right, so what we're going to do, we're going to now try to include some additional outside potential. So this would be things like maybe there is a concentration difference between the two systems, but there's going to be something involved that's actually forcibly trying to keep that concentration difference. So going back, maybe it's something like a battery that's pretty much forcing the chemical potential. The only thing that I can really think of, off the top of my head, would be something like a capacitor. So normally the capacitor would always a capacitor wants to have no charge on each plate, but when you attach a battery to it, you basically force there to be a chemical potential difference between the two plates. So that would be what we say of adding in an outside potential. So the two systems are going to be initially in a thermal equilibrium state, so their temperatures are going to be the same, but they will have a difference in chemical potential. And what we're going to say is that it doesn't really matter which one's which, but system two is going to have the higher chemical potential, such that the initial difference in the potential is the difference in their initial potential. Yeah, I mean, I guess I don't really need to explain that one. All right. So, in order to actually get this chemical potential difference, we're going to actually have to add some sort of, in this case, we're going to be talking about electrical stuff. We're going to have to add some sort of potential difference so that the two systems will end up being equal. Um, so, what we're going to say is this, that the chemical potential difference is equal to Q delta V. This comes from the amount of energy needed to move a particle between a potential difference. So that's really what this is. Even though we're calling this chemical potential, I guess it would be more like easier to call it a potential energy difference. I think we're trying to avoid the use the word of energy, but it is a type of energy. So the potential energy difference between the two systems will end up being equal to the amount of energy that is needed to move a charge between the two electrical potentials. So this is just another example of pretty much what I was saying before about how, if you have two systems, um, you can actually create this potential difference that you want by adding a battery in such a way that it forces it to balance out the potential difference. So here we have a high potential here. I believe that it's drawn like this. This is supposed to be the high potential, and this would end up being the low potential, and that this is set up to actually maintain this so that it almost like it balances out the potential difference by also including in this potential difference. All right, so the total chemical potential is going to end up being the sum of the internal chemical potential and the external chemical potential. So this is what we're defining as the total chemical potential of a system. Now, we already know what the internal energy is, or the internal chemical potential is. That's that tau ln of n over n cubed equation. This one, on the other hand, will be dependent on what the outside potential setup is. So, for example, when it came to the battery, this would be the Q delta V equation. But let's say the thing that's maintaining the concentration potential difference was gravity, then this would end up being the gravitational potential energy between the two systems. So this mu external is really dependent on what exactly is acting as our outside potential energy system. You'll see what I mean in a second, but I just want to point out that the internal one is always going to be that tau ln equation that we got before. All right. So yeah, this pretty much says the same thing, that this is the tau ln equation that you got before. All right. So going back, when we have the two systems in equilibrium, their chemical potentials will end up being equal as well. So that means that we can end up having in situations like this, or that the change in the external potential is going to be equal to the change in the internal potential. This becomes a lot more useful, mainly because, like I said, going with the whole idea or the concept of the external being something like the gravitational potential energy difference or the electrical potential energy difference from a battery. For the most part, you're always talking about a potential difference for those. So it's more useful to use something like this and already include this as being your MGH rather than having like a MGY1 and MGY2 here, and it end up being more confusing than it has to be. So this could be a nice useful thing later on when you're trying to figure out the uh, uh, how to get it to equilibrium. All right, so here is a practice question where you can actually work on this stuff. Pause the video, work on this stuff, and we'll go over in a second. All right, so here we're talking about the Earth's atmosphere. It's got different isothermal layers, meaning their temperatures are the same, and they're in diffusive equilibrium. So they tell us that the potential energy is based off of the ground, where the ground is going to end up being zero. So right off the bat, we already know what the external energy should be. It should be some sort of gravitational potential energy. It even says as a function of height, which always in my mind leads towards the idea of gravitational potential. So they want us to figure out the concentration as a function of height and the pressure as a function of height. So what we're going to say is this, that we know that the chemical potential at the ground is going to be equal to 0 plus whatever the concentration is at the ground. So we have this for the first part. For the up at some height, we have mgh being the external gravitational potential, and then the other concentration potential equation. And since it's in equilibrium, we could set them equal to each other. So all we have to do is move this over to here. and start solving this. The good thing is that when we move it over here, because these are two ln terms, we can combine them together, combine their internal parts together into one ln term. And that would also actually get rid of the NQ term. I know it's a little hard to see, but this should end up being N0 divided by, uh, actually, I can't really read that. I want to say it's, oh, I think it's NQ. That's it. So this is N0 over NQ. Instead of combining the ln terms, I guess I just threw in the E just to get rid of them right off the bat. Doesn't matter. Would have gotten you the same thing either way. But what you end up getting for the function of the concentration as a function of height is this. So it ends up being N0 E to the negative mgh over tau. Now, I do want to point out one thing. Even if a question doesn't ask you to solve in algebraic terms, which for the most part it really should, I don't really see a whole lot of questions that don't really ask for it. Um, it's always good to write in variable terms, because one thing that you'll start to notice is that there is going to be a pattern in this setup, because for the most part the ground state should pretty much almost always have an external potential of 0. So it'll always pretty much, or I shouldn't say always, but so very commonly set up like this, where you have the internal concentration potential at the ground state, whatever the external potential energy is over here, and then the concentration at whatever the final spot is. Now, to do part B, we're finding the pressure. So we know that pressure and the number or the concentration are going to be directly proportional. So this actually just comes from the ideal gas law, but just written in a slightly different way. If you don't remember, basically this N is being replaced with capital N, the number of molecules divided by the volume, and the tau is replacing KB. So, sorry, not KT. So this is essentially saying the pressure is equal to the number of molecules times the Boltzmann constant times temperature divided by volume. But doesn't matter. All that matters is this: is that there is a direct proportional relationship between pressure and number of molecules. So we can pretty much just add in, replace the n's in our equation with p's, and there we go. Easy peasy lemon squeezy. Now, this actually is something that gets used a bit, sometimes called the barometric pressure equation. Typically, it gets rewritten and simplified to look something more like this. However, where HC is combining the mg over tau and is relating to what they would call a characteristic height. Now, the one thing though is that this is a considered an ideal case scenario, a good approximation of what's going on, because as we all know, the atmosphere isn't isothermal. There are going to be different temperatures as you go up. So this is not taking that into account. So yeah, this is a much more simplified version of what what you would normally use. All right, here's the next question. Pause video, work on itself, and we'll go over in a second. All right, so here what they want us to do is they want us to start with the partition function, go through that process to get the free energy, and then come up with this equation, essentially. So the partition function, as we know, is going to be E minus the energy divided by tau. Now, the energy here is made up of two parts. It's made up of the base energy that we normally have, but then also the gravitational potential energy of each molecule. So we can split the E terms to look like this. This part is going to be the partition function. This part's not really a part of it because this summation If you remember, it's as a function of the states. That's dealing with this part, not with this part in particular. So we can actually just replace this entire sum with the partition function, the base partition function. Going back and using the equation relating this to the free energy, all we have to do is take this equation and take the ln of it. So we have the ln of the base partition function plus this part, so just getting rid of the e. And it ends up simplifying to look something like this. Now we can actually combine this into F0 as setting it almost equal to, say, it's the base free energy, the initial free energy. And then, as we know by definition, the chemical potential is defined as the partial derivative of the free energy with respect to the number of molecules. So from there, this partial derivative will end up going between the two parts. The one that goes to here, well, this will just turn it into the initial potential, because that's what chemical potential is defined as. And then when it goes over to here, that the variable n is right here by itself, so it just kind of crosses out, and then we're left with mgh. So we end up getting this exact equation that they wanted. All right. So yeah, we end up getting the same thing regardless of which route or which method we take to it. Here's the next question. This might be the last one for the video, so pause the video, work on this up, and we'll go over in a second. Alright, so now what we're going to do is, so this one is a little bit more complicated. We're going to have to set up some stuff a little bit, but now what we're talking about is magnetic field energy. Here we have the particles can either be spin up or spin down. The energy for the spin up is going to be set up as negative mb, and the energy for spin down is going to be plus mb. And we're going to set the initial concentration to be when b equals 0. So they want the concentration as a function of b. Now the hint is that we want to figure out the number, the concentration of spin up and spin down separately before we end up taking it all together. Very common thing with these questions that you always want to try and split it into more manageable parts. You don't need a steak all in one bite. Alright, so we know that the chemical potential for spin up is going to be set as this. The chemical potential for the internal and the plus the external. So what that gives me is this. So this is my internal chemical potential, and then this is the external magnetic energy. And we know that this, for the spin up part, will end up being equal to this, the initial concentration, the initial chemical potential of the spin up. So this is what they mean by do it separately for spin up and spin down. So from here, I can then copy the same thing for spin down, just replacing all the downs, the up symbols with the down symbol, and then changing the sign on here because of what they said up there. Then from here, I can analyze them both the same way. So once again, we pretty much analyze it just like we did last time, where we raise every term to the power of e, and then simplify, and we should get something like this. So before we continue, I just want to note what I said before about, recognizing the pattern. You should have already realized that the exponent above the e will pretty much always end up going to be negative of the external energy divided by tau. So an easy shorthand to do some of these questions. Though on a test, I would like you to start and derive it from the beginning rather than starting from over here, because I would always, if you start from here, my big statement would be, well, how do you know? How do you know it's set up like that? So I would always recommend, starting from here, but this would be a nice way of kind of double checking and say, okay, is this the negative of the external? Yes. Is this the negative of the external? Yeah. All right. So now what we can do is we can start combining some of these terms together. Like for example, initially we know that the initial number of particles spinning up and the initial number of particles spinning down will add together to get the total number. And we know that the chemical potential of the spin up and spin down will end up being equal because it's in equilibrium. So what that means is that this can be rewritten as being 1/2 of the original number of molecules. All right, or the sorry, 1/2 of the original concentration. So then from there, we can actually finally get the final answer by saying that the concentration as a function of the magnetic field will just be the sum of these two equations, which we can actually simplify a little bit by pulling out a 1/2 and 0 from each term, leaving us with this. Now, on a homework or on a test, I'd be perfectly happy with this as your final answer. But if you want to go take it one step further, and I would recommend that you try to consider it. Of course, if you're gonna have trouble with it, don't do it. But I would have you. I would recommend that you try to think about it. But what you can do is combine this into this, the form of the trig function that ends up being equal to these two terms. This is going to end up being nice in some of the later parts, as you'll find, because it will make some of the derivatives that we end up having to do, or some of the other math that we end up having to do, a lot easier than working with this. But like I said, on a homework or on a test, I would accept either of these as the answer. All right. So I guess I'm going to pause the video from here. We'll continue with a few more questions on chemical potential, and then we'll probably have another video talking about Gibbs distribution later on. So if you have any questions, please let me know. Otherwise, I'll see you later.